Hi everyone, this is Swati and I'll be going to the starter notebook for homework 4P2. As you all know, this homework deals with implementation of an attention-based end-to-end speech-to-text deep neural network. Our main aim is to implement an attention-based system which solves the sequence-to-sequence problem. As you might have seen in all the previous homeworks, we have a vertical architecture where the input is passed sequentially through several layers until the output is computed from the final layer. But in this particular homework, we have the sequence-to-sequence problem where there is no input and output correspondence. In such kind of a situation, we have an encoder-decoder architecture which contains two separate modules, an encoder which processes the input and a decoder which generates the output. And these two are linked together through an attention module. So what does the encoder actually contain? The encoder basically takes in the input feature vectors and produces a high dimensional feature representation of the input vector. The input features have strong structural correspondence with the adjacent vectors that is in its neighborhood, and also there are certain long-term contextual dependencies with distant vectors. So usually the encoders contain CNNs and RNNs. CNNs are mainly used because they have the ability to find the structural correspondence between the adjacent or neighboring vectors, and RNNs are used because we have to capture long-term contextual dependencies. Then we have the decoder. The decoder mainly uses the feature vectors that are produced by the encoder, and it is used to produce an output probability distribution over the output sequence. And then we have the attention module. So the attention module can be seen as a module which creates a weighted sum of the sequences of the encoder representation vectors, and the weights with which the vectors are combined is in such a way that the context pays most attention to the most relevant part of the input. So we will explore the ways of computing attention where the network is able to learn these weights to give most attention to the most relevant part of the input for each of the output sequence. So in this homework, the baseline architecture that we are using is the LAS paper. It is the Listen, Attend, and Spell paper by Google Brain. The listen module is the encoder, the attend module is the attention mechanism, and the spell is the decoder module. And as we always tell you, you please get started early, and this homework will take significant amount of time in debugging and getting the pipeline working. And also this is the hardest homework that you would encounter in this course. So please do get started early. And the models also typically take longer time to converge and produce good results. The training time is a lot more compared to homework 2P2. And this homework is like the true litmus test for this course. So please do get started earlier. So let's go through the starter notebook. As usual, the starter notebook is very similar to all your previous homeworks, where we have the data set. In this, the data set is very similar to homework 1P2 and homework 3P2. The input contains a sequence of 15-dimensional MEL spectrogram vectors, and the corresponding output contains the output text transcription. The transcriptions have 30 characters, that is 26 characters from the English alphabet. And then we have the blank space, the comma, and two special characters, that is EOS and SOS. So totally the output dimension of your model would be a 30 character output, which is nothing but the probability distribution. And we also provide the vocabulary map where you have to use the indices, the char to index and index to char mapping. And then we have the data loader. Data loader is to divide your entire data set into mini batches and load them onto the module. And then the model. So in the model, we are going to implement the baseline model, that is the LAS, and the encoder. So in the encoder, we are going to have CNNs, LSTMs, pyramidal by LSTMs. And then we have the attention mechanism, where we implement the single head attention and the multi-head attention. The decoder contains the LSTM cells. And then we write the pipeline for training, and then we write the pipeline for inference. So let's quickly go through the starter notebook. So the homework write-up is put up on Piazza. Then the Kaggle competition link is provided. Kindly join the Kaggle competition. Uh, and then go through these two papers. The LAS paper gives you the model architecture, and the attention paper will help you understand what the single head attention and multi-head attention is. So these are all your initial setup. We're going to be using Levenshtein distance as a metric in this homework, which is very similar to your homework 3P2. And then we import all the necessary libraries and our configuration. Feel free to change the configuration and train for longer epochs if you want better convergence. We usually start with the learning rate that has been provided here. So yeah, we provide a toy data set, which is very essential for you in this homework. This is just to make sure that you're able to get a attention diagonal and just to get your pipeline working. Kindly proceed with the actual training only after you got a diagonal attention in the toy data setup. And it is to be noted that the toy data setup is just for a reference. The hyperparameters that you're using here is not necessarily the same hyperparameters that you should be using for your training. It could vary. So this is for loading our toy data set and creating the data loader. The vocabulary map is for your correspondence between your character to ID and ID to character. Kindly use the vocabulary map for all the transcript processing. Here, this is a toy dataset class that is provided. And this is the Kaggle setup, just to download the actual data from Kaggle. Like I said, the vocabulary map contains 30 characters, 26 from the English alphabets, the blank space, the comma, and two special characters, the EOS and the SOS. And the vocabulary map is provided here. This is for the character to index and index to character mapping. Here in the dataset and data loader, this is very similar to your homework 3P2. You can feel free to use the same code. And in the dataset, you can implement the substral mean normalization. It's recommended that you normalize all your inputs for this homework. And so in your data loader, in the collate function, the outputs are different for different inputs. And when you're using a mini batch, we cap the maximum length of your generated output to 600. Since for training, we have the transcripts and the transcript length. But however, for test, since we do not have any transcripts, we recommend that you use a maximum length of 600 for generating your outputs in the test and the validation data. And the model, as I mentioned earlier, the baseline approach for this assignment is derived from the LAS paper. It describes an encoder-decoder approach. The listener listens to the audio. The decoder it spells out the transcription. That's why it's called as a speller. The attend is, of course, for the attention module. And the listener mainly comprises of pyramidal bi-LSTM network. It takes the input audio feature vectors of the given utterances and outputs a sequence of high-level representation vectors that is approximately at the same rate as expected out of the speller network. The speller network takes the high-level feature output from the listener network and uses it to compute a probability distribution over sequence of characters using the attention mechanism. We can look at attention as it is as an intuition of understanding or trying to understand and learn a mapping from word vector to some areas of the utterance map. So a word which is at time step T8 might have a long-term dependency on some input feature vector that is at time instant T0. So that is why this attention module is used, so that we are able to focus on the parts that positively correspond to the output probability distribution of that particular transcript. So we elaborate that you implement this LAS baseline architecture, but however, you can use other methods and try various other things, and you can feel free to develop your own module and write a notebook from scratch. So the listener, that is the encoder. The encoder actually contains a base LSTM and a baby LSTM, pyramidal bi-LSTMs. The listener typically contains 1D CNN layers, which captures the structural dependency between the adjacent vectors in the input. And then we have bidirectional LSTMs, which capture long-term contextual dependencies. And we have a new variant of bi-LSTM called as the pyramidal bi-LSTM. Pyramidal bi-LSTM can be seen as CNNs with a stride equal to 2, which reduce the time resolution of the input by a factor of 2. So the pyramidal bi-LSTMs downsample the inputs by a factor of 2. It is either by concatenating adjacent pairs of inputs before running a conventional bi-LSTM on the reduced length sequence, or it could also be averaging the two adjacent vectors and passing it to the next layer. But however, we recommend that you use concatenation of the adjacent vectors instead of averaging them. So in pyramidal bi-LSTM, say for example, we have the input sequence as batch, time, 15-dimensional vector. The input to the next layer would be batch, t by 2 and 15 into 2. The feature dimension size increases because we're concatenating and we're reshaping the output from the first layer. So there are two approaches. One is you can concatenate them or you can average them, but a suggestion would be to concatenate them so that we retain all the information in the sequence. And also we reduce the rate. And so we basically suggest having a baseline bi-LSTM and then 3 layers of PB-LSTM, which reduces the time sequence by a factor of 8. There can also be other CNN networks that could be used here in the listener. You can replace the 1D CNN network with your ResNet blocks or Connext blocks from your previous homework. But the baseline LAS paper just has the LSTM and PB LSTM. They do not have any 1D CNNs. You can always feel free to explore that dimension. We write the forward function here. So the forward function is again similar to your homework 3P2. pad the sequence, pass it through the LSTM, then pad the pack sequence, pass it through your pyramidal by LSTM layers. So this is the encoder. We initialize the listener here. And then next we have the attention block. So a typical implementation of attention block is by having the key value and query projections. So we project our embeddings from the encoder and through a linear transformation and compute the key projections. And then similarly, we have the value projections. The embeddings are passed, are linearly projected, uh, and we compute the value projections. So the weights, WK and WV, that is weights for the keys and weights for the value, are learnable parameters. For each output produced by the decoder computes a query. It is a query to the attention module. The attention module uses this query and the keys K to compute a set of attention weights. This attention weights should strictly be non-negative and must sum to 1. And they are typically computed by a softmax applied to the normalized inner product of query and the key. And then this is used to get the context vector CK, which is nothing but your weights WKJ multiplied by your values. So this context vector uh, actually contains the portion of the encoded embeddings, which most positively correspond to the output that is produced at that instant of time. So we write the key value and query projections in the softmax here. And we have the forward function for this. The pseudocode for attention is been provided in the handout. So please do go through that. And then we have the speller. Speller is the decoder architecture. The main purpose of the speller is to provide a probability distribution over the output sequence. Here, the speller is autoregressive in nature, which means that the output from the previous time step is fed to the next time step for predicting the sequence of outputs. And here we have the LSTM cells. We cannot directly use the LSTM layer. You're supposed to be using the LSTM cells according to the LAS architecture. And then you have to run a for loop over all your time steps in your forward function to pass your embeddings through the decoder for the entire time sequence. So when we use this speller, we also pass the attention module here. And then we return what are the predictions in the attention plot. Our LAS model, here we initialize the encoder, we initialize our attention module, we pass the attention module to the decoder, call the forward function here. This is the model setup. We initialize our model, define what is the embedded dimension size, what is the input, what is the output size, etc. And then here we are defining the optimizers. The optimizers that we recommend using are ADAM or ADAM-W. The loss that we're using here is cross entropy loss. If you want to have mixed precision training, then you can use the scalar for mixed precision training. But make sure you're using the scaling properly. Kindly go through the PyTorch documentation for the scaler. And yes, so here we introduce another concept called as a teacher forcing. So teacher forcing can actually be viewed as a gate which controls the percentage of ground truth that is being fed into the network, and also the auto-regressive input that is fed into the network. Since our decoder is an auto-regressive network, in the initial stages of training our model, the output that is produced by the decoder is erroneous. So having passing an erroneous input of the previous time step to the current time step can lead to faulty prediction at this time step as well. So that is why instead of feeding the previous time step inputs, we feed the ground truth inputs in the initial stages of training. So this teacher forcing is when the teacher forcing rate is set at 1, the ground truth is only fed into the network, whereas the auto-regressive inputs are cut off. As we reduce the teacher forcing rate, the previous time step inputs are being passed at a higher weightage in contrast to the ground truth vectors. So this helps the network to perform better as we keep training the model. Uh, so initially, the teacher forcing rate should be 1. As the loss decreases and as we approach good convergence, the teacher forcing schedule is reduced. So you can have your own custom class for a teacher force rate scheduler. And after that, here we have the Levenshtein distance. Levenshtein distance is basically the number of modifications that you need to make for your predicted sequence to match the ground truth sequence. So the Levenshtein distance is calculated here. The Levenshtein distance for each transcript is calculated, and we average the Levenshtein distance per mini batch. This is the training loop. We take our MEL spectrogram and then we take the transcript, pass it through our model. And here, just be careful when you're using the mixed precision. Make sure that you unscale the optimizer first before doing the gradient clipping. You can use gradient clipping to prevent exploding gradient problems. And now we have the validate function. This is the inference. This is for plotting our attention. We can save our model and save our checkpoints if our validation distance is less than the best Levenshtein distance that we have obtained so far. And then you can write the code for testing here. This can be very similar to your previous homeworks. So some debugging tips. So make sure that you use the toy dataset. Ensure that you have attention plots that are diagonal like this. Use mixed precision training so that you improve the training time. So there are two ways of approaching this sequence to sequence problem. One is word based and one is character based models. The word based models won't have incorrect spellings and are very quick in training. But however, the problem is they cannot predict rare words. So we refer that you use character-based models. Even the paper also prescribes that you use character-based models. Most of the TAs are familiar with character-based models, so you can receive more help if you stick to character-based predictions. And then when you're processing the transcripts, use the vocab map that has been provided for index to char conversion and char to index conversion. And then use the built-in PyTorch libraries, the pad packed sequence and pack padded sequence. Use the enforce sorted equal to false flag just to make sure that you don't want to sort the inputs for every batch. And then you can experiment using CNNs over pyramidal bi-LSTMs. You can use ResNet blocks, ConNet blocks, or MobileNet. Feel free to explore various other CNN architectures, but just make sure that you don't downsample your input vectors below a factor of 8. And then the pseudocode for single head attention has been provided in the handout. You can follow them. And similarly, multi-head attention. Multi-head attention is having various single head attention blocks right after the encoder and concatenating all of these and passing it through the linear layer to give us multi-head attention. So in inference, we want to select the most probable output sequence. So there are three methods. One is the greedy search, but this greedy search is very time consuming. Then we have the random search. A random search might or might not give you the most probable output sequence. And then we have the beam search, which iteratively expands out the k most probable paths until you encounter an end of sentence. And then we have Levenshtein distance. In the Levenshtein distance, you do not use the EOS and SOS. There are other weight initialization techniques that you can use, like the Xavier initialization or Kyming initialization. And for regularization, we can have dropouts, log dropouts, wait time, and embedding dropouts. This is similar to what was told in homework 3P2. And feel free to use data augmentations, the time and frequency masking. Optimizers, as we have suggested, we use Adam and Adam W and use weight decaying parameter. Actual LAS paper has a SGD, but we suggest Adam and Adam W, but you can always try ASGD. The learning rate scheduler, the learning rate, initial learning rate is 1 e power minus 3. Try using different schedulers. You might have already used the reduced alarm plateau and cosine annealing exponential LR scheduler, etc. So you can try them. The last part is pre-training the listener. The listener can be pre-trained using an autoencoder architecture separately. The autoencoder contains a separate encoder and decoder block. You would pass the audio input to it to get a high hidden representation. And you can use this pre-trained listener so that you'll have a better convergence. And we can also pre-train the speller. You train the transcripts as the trained data and train your model like you would train a language model as it was covered in work for P1. Yeah, I think all of these should definitely help you reach high cutoffs. I can't stress much more than this, but please do start early because this is one of the most hardest and challenging tasks in this course. Thank you.